All right. Good morning and thanks for coming. Today we're going to dive into Chrome exploitation. We go through the inner working of Chrome's architecture, focusing on the V8 JavaScript engine and its exploitation pathways. Right, let's get started. So, let me see. Yeah. All right. My name is Matteo Malvica. I'm a content dev and researcher at OffSec. I'm Italian, living in Norway, and occasionally I play drums in a local band. So that's the agenda for today. We'll start by exploring the Chrome architecture and the V8 pipeline to set a foundation for understanding how things work under the hood. Then we'll look at vulnerability class named Type Confusion, which will serve as a stepping stone into discussing our three CVs for today. The first one predates the V8 Heap Sandbox. Then we move to the modern sandbox era with the second CV. And then we wrap it up with the third and last one, CV, which serves as a fresh example of present-day vulnerabilities in Google Chrome. For each one of this bug, I'm going to demonstrate a Windows-based exploit, and for the last two, I'm going to show how also we can bypass the new Heap Sandbox as well. So why it matters? First of all, browsers are one of the most used software worldwide, so meaning they are a really valuable target. They're always connected, so it means if we can exploit vulnerability in the browser, we can get remote code execution to some extent. Browser also demands speeds, meaning that we need to serve fast every day. Many different tabs open at the same time, right? And that's why we have JIT compilers. More on that later, but JIT compilers basically helps browsers to be fast. And JIT compilers are also very complex software, meaning that will lead to bugs, like most of the complex software will do. So today's focus is on Chrome, and specifically its JIT engine, V8 on Windows. Why Windows? Because it's one of the most widely deployed operating systems in the world, and it's very enticing during red teaming. So yeah. Let's now get a brief overview of the Chromium architecture first. Before we jump headfirst into vulnerabilities, let's see how Chrome works behind the scenes. So, like many browsers, Chrome uses multiple processes. The main process communicates with the isolated renderer processes through IPC or inter-process communication channel to keep them all the processes separate. So, but what's the renderer process? Basically, the renderer process handles JavaScript, DOM, and CSS rendering, and it's the most vulnerable as it processes untrusted code, untrusted JavaScript code, right? So, to protect it, Chrome uses a process sandbox, which is outside the scope of this talk. So, if I'm talking about sandbox from now on, it's the heap sandbox, not the process sandbox, which is I'm not talking about this today. So historically, gaining code execution on the host required two bugs. One in the renderer process and one sandbox escape, right? And then you could get a full remote shell. But now with the new V8 Heap Sandbox, it's more complicated. So we need three CVs basically: the renderer, the Heap Sandbox bypass, and the process sandbox bypass, right? Cool. But before analyzing the first bug, let's zoom in and get more familiar with V8, the Chrome JavaScript engine. So first off, let's get a bird's eye view on the V8 pipeline from a high-level perspective. So any modern JavaScript engine consists of several key components. The parser, which basically processes the source code of JavaScript, and it breaks into tokens and generate an AST, an abstract syntax tree. And it's what the abstract syntax tree does, basically tokenize the code, the source code, into fundamental Unicode. Like, for instance, a line of code like let x equal 10 will just result in 4 different units of code. And from that, we build the AST, which is a tree structure that represents the code syntax and the relationship between the different unit of code. From that, we have the interpreter, which basically takes the AST the syntax tree, abstract syntax tree as an input, and then it generates bytecode, right, for execution. So basically, older browser would just have an interpreter and just execute whatever JavaScript code in the interpreter, right? The bytecode itself, it's an intermediate representation of the program that is designed to be executed in a virtual machine. And recently, in the last like 10, 15 years, probably even more recently from browser history perspective, we also have a more advanced compiler called JIT compilers, which are basically optimized compilers. So they takes the bytecode in, basically, and try to optimize the resulting machine code for a more efficient execution. The actual version of the V8 pipeline from 2022 is here, so like 2-3 years old. That's actual V8, how it was working 2-3 years ago. And we have the interpreter, which is named Ignition, and then we have Sparkplug and TurboFan, which are two compilers, the JIT compiler. Sparkplug is a non-optimized JIT compiler, and TurboFan is the optimized JIT compiler. More on TurboFan later on today. The relationship here is that Ignition works with something called the profiler, so it analyzes the JavaScript function at runtimes, profiles them, and in case it deems that a function calls many times, it might mark that function as hot function. So that's called hot code, meaning that it triggers TurboFan to compile that function into more optimized code, since we're executing the function many times. So more on hot function and hot code later in a second. That's the actually it's 2025, so it's the same from 2024. That's the up-to-date pipeline that we have today in Chrome in V8. We have a new compiler called Maglev, a new JIT compiler. So in December 23, Maglev has been introduced and acts as a compromise between Sparkplug and TurboFan. So we have a 4 tiers pipeline now, and Maglev sits basically in between the non-optimized compiler Sparkplug and TurboFan, which is the most optimized JIT compilers. And we'll more on Maglev on the last bug that we're gonna see today. So that's zooming into the 4 tier compiler pipeline. So we basically see that we have Ignition, Maglev, TurboFan, and Sparkplug. The Ignition and Sparkplug, they're unoptimized, while Maglev and TurboFan are optimized. So whenever the compiler decide that the code execution require optimization, so they will just optimize it, and likewise they will like switch back to unoptimized code in case that there's a need for that, right? So it's everything happens at runtime, and depending on the JavaScript code that we are processing, the profiler helps in deciding which compiler is going to execute a specific piece of JavaScript code at runtime. So having a bit of a review of the V8 pipeline, so let's now see how JavaScript gets actually executed inside V8. Ignition is not optimal as it doesn't generate efficient machine code, but even though we have like the interpreter, as we said, is named Ignition, so it basically execute. It's the first stage of executing code inside the interpreter, right? So we execute JavaScript here, and what the interpreter does, it takes bytecode as an input and execute it via the JavaScript virtual machine. That's what the interpreter does. And the virtual machine is responsible for generating and executing machine code, right? So let's see how actually JavaScript bytecode looks in reality. Here we have an example of a function that adds to whatever number we are passing as a property, right? You can see that we have something called D8 here. So whenever we want to work on V8 on the JavaScript engine, we don't have to compile the entire Chromium, right? Because it normally will take a few hours on a beefy laptop, right? So we could just compile V8, and together with V8 we have something called D8, which is the debugger. So we can just debug V8 as a standalone mean just by using D8. So we can test any property, any feature of V8 just right inside D8, and that works both on Linux and Windows, and on Mac of course as well. So back to our JavaScript bytecode function. So here we can print with D8 the resulting bytecode. So the first instruction basically loads 2 into the accumulator, which is A, load A, the accumulator. It saves it into, then it saves whatever value that is in the accumulator into register 0, R0. And then we load the function argument A0, the first argument, into the accumulator. Next, we add R0, whatever we saved R0 to the value into the accumulator, which is 13 in this case, because we are calling the function with 13. And then in the end, we return whatever we have in the accumulator to the calling function, which is 15. This is a very straightforward example of JavaScript bytecode. So just-in-time compilation. Again, the interpreter generated code is not actually optimal, since it works inside a VM, so it requires an abstraction layer, and it's not optimal for some kind of function that requires more performance. But how do we solve this? With we mentioned before is just-in-time compilation. So if we want to produce more efficient machine code in memory, then we need some kind of different compilers. So if a unit of code is executed more frequently, we can move this function to higher compiler tiers, and then produce better machine code at runtime. Now we can take a look at JavaScript object, how they can be represented in memory, and their values types, right? So first off, how do we store type information in JavaScript? So since JavaScript is a dynamically typed language, the engine must associate type information with every runtime values. And in V8, this is achieved using combination of pointer tagging and dedicated type information objects called maps. More on that later. And notably, memory, small integers known as SMI, have their least significant bits set to 0, while pointers to heap object have the least significant bit set to 1. So this is a way to distinguish between SMI and basically JavaScript object. And this is actually pointer tagging in action. So again, we mentioned that JavaScript is a loose-typed language. So unlike C or C++, when we compile something in C++, like this function, we can get more or less deterministic assembly output, right? That's what happens with compilers. And on the other hand, with JavaScript, we have a function simply takes two objects and adds them. What's the result of this at compile time? We don't know, because types can change at runtime. That's how JavaScript works, unfortunately. But that's how it is. So it's impossible to determine the program's exact behavior at compile time, but we are allowed to infer the types at runtimes instead. JIT compiler doesn't know how the data types in advance, but it can learn from past runs and guesses how the code will be used in the future. So that's how the JIT compiler works with the profiler. And it makes some kind of optimization based on those assumptions with the profiler, and like creating faster code, assuming that those types will stay the same over time. But how does the JavaScript engine, in this case V8, keeps tracks of those data types at runtimes? How can we do that? With something called maps. So maps are also referred as hidden classes. in the JavaScript official terminology. In SpiderMonkey, the Firefox JIT engine, they're referred as shapes. In JavaScript core, Safari uses butterfly structures, and Chakra, the old Edge, used hidden types, not confusing at all. So, but here Chrome Google decided to call them maps, right? So we stick with this terminology for today. And so in this example, we have an object, and we add two property, and we assign two different values to these properties, x and y, of 1 and 2, right? And again, with D8, we can inspect those property, right? And we can see how those properties are mapped in memory, right? They have those addresses. So let's see what happens when we add another object with the same type but two different values on the new object. So the surprise here is that they share the same addresses. Why? For efficiency. So if we have two objects sharing the same types, they will also share the same maps in memory. So this is not to clutter memory with so many maps and many different data structures. So this is a means of optimization and memory efficiency. They both share the same map and fixed array in memory, these two objects. So that's a cool feature of maps. So let's zoom in on TurboFan. We mentioned TurboFan earlier. And TurboFan, it's the most optimized JIT compiler. And on top of Sparkplug and maglev, the new compiler, it basically converts the bytecode to a custom intermediate representation, or IR. The IR is basically a graph made of three components: nodes, which are basically the operations, and contraflow edges, and which are contraflow edges, obviously, like for any functions, and dataflow edges, which are the inputs and the outs of the functions. So let's take a look at how TurboFan pipeline works from a high-level perspective now. So first of all, what TurboFan does is to build a graph. It analyzes the bytecode at runtimes and makes speculations and about whatever operation the function it has to do and what types are involved. And it tries to have some kind of safeguard with something called speculation guards, because we mentioned that JavaScript can change. It's dynamic, so types can change. So TurboFan puts something called speculation guards to prevent that if a types will change, then what we do is to roll back to non-optimized compiler. So basically we go back executing bytecode in the interpreter. Why is that important? We'll see that later, because if we start executing optimized code without speculation guards, we might risk bugs. Whenever we have built our graph, we can start optimizing code with the JIT compilers. So it basically transform and optimize the original bytecode into more optimized code in memory without affecting correctness. And the last phase called lowering, which basically writes the optimized code into memory. That's how TurboFan works in 3 steps. Right. A quick JIT example. So we mentioned hot function at the beginning of this presentation. So here's an example of a hot function. We can always test this in D8. So we execute this function basically 10,000 times, and most likely the JIT compiler will pick it up. So TurboFan will pick it up. So and with calling this function 10,000 times, we have dynamically created objects, and we made the function hot, which, as we said, will trigger JIT compilation. So let's see how this will have an impact with speculation guards. So we mentioned that TurboFan will generate some speculation guards. So we'll put some speculation guards in the optimized code. We also have maps that stores the type dynamically. So we have maps that keeps track of those types changing at runtime. But we have no guarantees that maps will stay the same for a given object in time. The interpreter will generate feedback that is used by TurboFan to make informed type speculation. So that's this workflow between the interpreter and the JIT compiler is really important to keep track of the data types of a JavaScript. And as we said, as we see in speculation guards are runtime checks, and those are really important to make sure that the optimized code doesn't take into account different types, basically. And if a failure occurs, then we de-optimize. That's two different examples of speculation guards. In the first example, we ensure that we are dealing with a small integer. So we are testing whatever value is in RDI, and if the last bit is not one, we bail out, basically. Has one, sorry, bails out. So meaning if we have a pointer, we bail out. And the second one, it checks a map. Checks if a specific map is assigned to the value that is in RDI register, right? And we are subtracting 1 to RDI because every pointers in the V8 is tagged with 1. So whenever we need to perform an operation with pointers, we need to subtract 1. And then we compare it with this dummy value, which is associated with a specific map. If not, then we bail out and we go back to the interpreter to execute this code in interpreter. This is again to avoid any consequence to the optimized code, which might lead to bug or vulnerabilities. Right. A specific case of these guards is called redundancy elimination, which is a popular class of optimization that aims to remove safety checks from the machine code if they are determined to be unnecessary. So on one hand, we have speculation guards. On the other hand, we have optimization means by TurboFan. So in practice, what we have is that if we have this function, we could have this resulting intermediate representation. But as we can see, the second optimization might be unnecessary, is redundant, right? The second check heap object and check map are redundant. So what does redundancy elimination, which is one of the optimization phases of TurboFan, is that it might remove it. However, are we really sure that we cannot have any possible side effect in between those elimination? Let's see. What could possibly go wrong? So let's introduce type confusion vulnerabilities. Right. So JIT engines are complex because compiling at runtime requires balancing speed, optimization, and secure coding. Bugs arise during JIT compilation due to most likely missing checks. So the JIT engine assumes that data is one type at compile time. However, at runtime, type changes without the related type checks. That's basically what leads to a type confusion bug, which also ultimately lead to out-of-bound read and then code execution. So let's now discuss the first of our 3 bugs, which it's really cool bug from 2018, pre-Heap Sandbox. This is very classic type confusion bugs in browser. So it's very typical and predates the Heap Sandbox. So we can get a sense on how V8 bug can get exploited without any extra mitigation. We're not gonna do into the nitty-gritty of every bug or every exploit, so I'm trying to keep it very high level now, because also we don't have much time in general. But that's the root cause for these CVs. So basically, this is part of the bug, the root cause, and we have the chain of write operator that states that the engine assumes that the operation will observe no consequence, no side effects. So whenever we call this create object with this no operator, we just say, "Hey engine, don't worry, the object won't change." Okay. Obviously, the object map has changed when becoming a prototype. So here, the function generates a new map for the object. So even though we told the JIT engine, don't worry, this is not going to change, but it does change. So that's the bug, basically. So the newly created object is converted to a prototype object, which also changes the object associated map. So the map changes without informing the JIT compiler. This is a very typical and seen side effect that the JIT compiler hasn't taken into account. So it's sort of a maps confusion. Here, we're going to demonstrate the root cause again in D8 in the debugger. First, we print the object memory, then we create the object via the vulnerable function, which is object create, and then we print again the object. So as we can see from D8, we have a map at this address of fast property types. After triggering the vulnerabilities, we have another types for the same map with the dictionary properties. So meaning the types has changed from TurboFan, from the JIT compiler perspective, even though the types in the function hasn't changed really. So we could abuse this fact by accessing memory out of bound. So we can obtain from this type confusion, we can obtain relative read and write. And then arbitrary read and write. This is typically way to exploit type confusion bugs. And how do we perform code execution? So V8 Heap has an X, so we cannot execute code or dep on Windows. So basically, the memory is either writable or executable. Yeah. So how can we execute shellcode if the memory is read-write? Let's introduce WebAssembly shellcode. So in the V8 heap, we also have memory region assigned for WebAssembly. And we also have jump tables that are referenced inside the V8 heap. So WASM is basically a binary format that can execute faster than JavaScript code, right? And it's compiled by liftoff, which is another V8 component. And inside the again, this bug is from 2018. So back then, the WASM jump tables were read, writer, and executable. So perfect to hijack code execution. And that's a brief demo of the exploit. Let's see if that works. So we have a shell on Kali, we execute on Windows, and we get a reverse shell. It's very high level. We don't need to go into all details of the exploit, but that's just to show you that it's working. Okay. Right. So pre-heap sandbox, what do we have? Basically, how do we exploit any bug in 2018-19? So pre-heap sandbox, we gain out-of-bounds access. We harness type confusion to abuse the object that is vulnerable, and then from that we gain arbitrary read and write, and from that we gain code execution by writing function pointers, as we just saw. So typically via WASM WebAssembly import table. Right, an important thing here is that normally when we try to build our primitives, out-of-bound primitives, we abuse something called the backing store pointers, which is basically a pointers in an object, in JavaScript object that reference actual memory region. So from that, we have basically the coordinates to build up and create arbitrary read and write. The second CV for today is from 2023, and it's where's the V8 Heap Sandbox was already rolled out. This has been discovered by Manu Umo, which is a vulnerability researcher from GitHub Research, and it's another type of confusion. Again, this time is in the maglev compiler. So I mentioned the maglev compiler has been rolled out in 2023, and like any new software contains bugs. So it's still possible to find bugs in maglev. But before analyzing the bug itself, let's first explore the whole purpose of the Heap Sandbox. So this has been rolled out by Samuel Gers from formerly Project Zero, now part of Chromium Security. And so as I mentioned earlier, up until 2023, we just needed 2 vulnerabilities to get full code remote execution on a system via browser vulnerabilities on Chrome. So on the renderer process and 1 sandbox escape for the process sandbox. Now with the V8 Heap Sandbox, it's becoming more costly. So we need 3 vulnerabilities: 1 on the renderer, 1 heap sandbox bypass, and 1 process sandbox bypass. And so how the heap sandbox works? So basically, the V8 heap is contained in a sandbox now, referred also a cage or Uber cage. So it's a predefined memory region. And this design ensures that any out-of-bounds access is confined within the sandbox. So what they try to achieve is to remove any kind of pointer. So all the pointers are being removed outside the sandbox. So we now have a pointer table, so only the offset of those pointers are stored inside the heap. And it's still software-based, this sandbox, not fully hardware-based, which is still not optimal probably. So at some point it will be hardware-based. And this has been rolled out in 2022-23. Yes, the main key takeaway is that we have a pointer table. So the back-in-store pointer that we typically have used before is not available anymore. So we don't have pointers. So in practice, here it is in yellow. So this is just a simple JavaScript array buffer that we are dumping. Pre-heap sandbox, we had the full pointers for the back-in-store pointer here. And what we have here is just an offset, 45C, which cannot be abused anymore because the pointer table lives outside the heap sandbox. So we cannot access that anymore. Sorry. So this bug, back to our bug, this again is a type confusion, this time in maglev, in the maglev compiler. Now, now that we have some background on the heap sandbox, let's see how this bug works. So, as mentioned, it's a new mid-tier compiler, maglev. It generates less optimized code, but it does that quickly than TurboFan. So it compiles quicker, and so for some use cases, it's better to use maglev, and for other JavaScript code, which requires more performance, then the profiler would suggest to use TurboFan. So this specific CVE was a check failure while initiating a specific object in the compiler. So as a result, the same map is used for a different type. So it's very similar to what we saw earlier. Yeah. So the standard WASM shellcode is not possible anymore due to heap sandbox. So on top of what we saw, like moving the pointers out, they also implemented other mitigation, like you cannot use WASM shellcode anymore. However, not every pointer in the V8 heap is an offset. So the heap sandbox is in context in continuous evolution and in constant improvements. So back in 2023 wasn't perfect. So not every pointer in the V8 heap is an offset. So they left some full pointers there. One of those are JIT compile function pointers. They were still present in the V8 heap back then. Solution: how do we deliver our shellcode? So whenever we start to exploit our bug, how do we deliver our shellcode? By modifying the function pointer to jump right into JIT Spring shellcode. What is actually JIT Spring shellcode? So let's see it in practice. Here at this point, we already abused the type confusion bug to obtain arbitrary read and write in the heap. And so how do we exploit it further to generate shellcode? This is a simple example. We have a function that returns 3 floats, 1.1, 2.2, and 3.3. And then what we do is that we trigger, from D8, we can trigger the JIT compiler with this special function. So prepare function for optimization, then optimize function on next call. So this will effectively trigger TurboFan. And then we print our shellcode and see what does it look in the debugger. So let's compile the code and see how it looks in memory. So that's a really ugly number here. So what's this? So we move this float into R10 register. What's that? Oh, it's our first double. So it's 1.1 that we define in our dummy function. So what are we going here actually with this? So what if we can treat this float data as code instead of just floating numbers? So let's revise this function to something different. We now have even more uglier floating numbers here. We have 3 floating numbers that doesn't look really anything reasonable from this output. But how do they look in memory? Let's see. So here we're moving another value, which seems different, into R10. If we disassemble this at this address, so at this memory address +2, we can see a breakpoint, a NOP, and a jump instruction. So we can treat this as shellcode, basically. And we can chain those instructions together and jump between each of these floating numbers, basically, in between. So we can jump between this move instruction. The only caveat here is that we have only 6 bytes for the shellcode at a time that we can encode. So it doesn't look really simple to do that. How can we automate the whole shellcode generation process? We have a simple Python tool based on Pwn tools. So we can just translate simple assembly shellcode into floating numbers, floating point numbers. Let's demonstrate now the full exploit with the second demo. Again, just from D8, not the full Chrome build. Even the first demo that we saw today was from D8. So whenever we have a bug that just is affecting the V8 engine, we can just test it with D8. We don't need to compile the whole Chrome build. Yes, so that's the resulting output from the Python script. So it just prints the 3 floats or even more floats that we need for our shellcode in the JavaScript exploit. So here we are just calling D8 with the maglev attributes. So we trigger maglev, we enable maglev, and we execute exploit, and we pop calc. Okay, with the new shellcode JIT spraying technique that we mentioned. Right, time for the last CV. So this is a present-day Heap Sandbox from 2024. Again, from Man UMO, so the GitHub researcher. This time his type confusion in object transition. So type confusion in maps handling via prepare for data property. So again, when an object structure changes, a new map is created. We have a bug because when this transition leads to type confusion, where one bug is expected, but another one map is expected, but another one is provided. So again, we have some sort of map confusion. So the JIT compiler thinks that the type, so the type stays the same, but another map is provided. So we can access memory that it's outside the original map structure, basically. With the new recent version of the Heap Sandbox, we don't have WASM function pointers anymore. So we had this in the last version. From the previous bug, we don't have WASM pointer anymore. They're fully removed from the V8 heap. However, V8 heap is only one part of the picture this time, so we need to be more creative. At runtime, we have other objects outside the heap that we can abuse. Blink object like DOM-rect are stored in Blink, which is the Chrome's renderer. Blink is responsible for rendering web pages like HTML, CSS, anything that is not JavaScript, basically. And those are outside the V8 heap, but referenced by embedder fields inside the heap. That's important, and we see why in a second. So basically, we can abuse the first type confusion of the CVE, and the second one, with this type confusion, we can trigger a second layer type confusion between blink objects, so like DOM-rect and DOM-type array, by swapping the types, basically, via these embedder fields that are referenced inside the V8 heap. So we can still generate WASM shellcode. With blink second level type confusion, we can gain read-write primitives outside the heap sandbox, right? We can leak then the base address of the trusted cage. Trusted cage is simply a data structure of the heap sandbox itself. Since we don't have pointer anymore, we need some kind of pointers to build our shellcodes, right? As also to bypass ACLR, obviously. And this is obtained via the second level type confusion. And since we have a reference now in the heap, we can identify the JIT compiler WASM that we have outside the V8 heap. So we are acting outside our heap with our exploit now. So the code pointer is overwritten by setting DOM-rect to a new WASM offset. So basically, we hijack our WASM shellcode and make it point to the function. So we're not going through the details of the whole exploit, but basically, under normal condition, calling the WebAssembly function alone wouldn't let us execute anything to be executed from the V8 heap. But now, since we have arbitrary code read and write, in Blink, so outside the V8 heap, we can do that because we have abused the type confusion bugs at the extent of bringing it outside the heap, the V8 heap, right? So to recap this exploit, which it's a bit more complex than the other two, we basically trigger the dual type confusion first via V8 and then via Blink, leak the heap address via the sandbox address. We identify the JIT function pointers, and then we overwrite the pointers. And as soon as we overwrite the WASM pointers, we can invoke compromised WASM function pointer as we did before. This is the last demo for today, and this one is going to be live. Before jumping into the actual exploit, I'll just show you how to convert regular ASM into shellcode into WebAssembly this time. We're going to use another way to generate our shellcode, not with the Python script that we saw earlier. So this is going to be live to a Windows machine that I have at home, so let's hope everything works fine. Yeah, I'm still connected. Good sign. So I'm not sure if you can see, but that's the final exploit. So we don't need to go into every details, but basically this is a WASM buffer. As you can imagine, this is the actual shellcode, the final shellcode. How do we generate that? So every D8 release or V8 has something called WASM module builder, depending on the version. We can use this WASM module builder to generate WASM code specific for the V8 version. So we can basically export a function and specify inline assembly instruction this way. So in this shellcode, what we're doing, we're simply retrieving the base for kernel 32 DLL in Windows, then find winexec and then pass calc. This is basically the string for calc, and then we pop calc this way. It's very simple, very straightforward. And then we call the address that is stored in RAX, which is winexec in this case. I just ported the shellcode for the latest Windows 11 version, so this works on the latest Windows version. How do we test this? For this time, I couldn't test this in just with the 8 of V8 as the previous two bugs. I had to compile the whole Chrome version because we are exploiting Blink objects. Blink are outside V8, right? So we need to run the full Chrome with no sandbox. As I mentioned, this no sandbox argument removes the process sandbox, which we haven't touched in today's talks, right? So we can test the full exploit. Right, and we also have a warning, you are using a support on flag. Yeah, of course. So it's normal. and from here we just load the exploit, and then we have calc. Cool. Yes. That's about it. So, a few key takeaways. So browser are complex, high valuable targets today's. It was 10, 15 years ago, still today. It's more complex to find bugs and exploit bugs. But type confusion bugs will likely persist in V8 due to the JIT engine nature. So JIT engines are complex. Microsoft has tried to remove Microsoft now in Edge. They're running Chromium version on Edge. They ditched Chakra a few years ago. Now they're running Chromium, but they did some modification to Chromium. They claim to have removed JIT. I don't know. But still, most of the world is using the Google version of Chrome, and this has now we have 2 JIT compilers which are optimized, maglev and TurboFan, and those compiler we're gonna find bugs no matter what, because JIT compilation is a hard problem to solve securely. But now they made these V8 Heap Sandbox, which is definitely increased the attacker cost, but it's not bulletproof as we saw. So now, if you're interested, the sandbox, the V8 Sandbox is fully promoted into the Google Bug Bounty program. So you can file actual bugs and get a bounty for that. So now 3 bugs are required to get a full system shell in browser, which is a game changer from a few years ago. You can find all the code for today's presentation here, if you want, on pocufo.org. Thanks for today, everyone. And any question? Yes.
So I feel like type confusion was like the biggest thing, right?
Yeah.
I just started thinking about languages like TypeScript, which is increasing in popularity, but at the same time it's just compiled into JavaScript.
Mm.
But I feel like there should be like some opportunity to put in some hints to the JIT compiler, so it can maybe predict what types an object should be instead of changing the maps all the time. Is that something people are looking at, or is it just me fantasizing?
The question is just let me repeat the question. If we can use TypeScript to improve the prediction of JavaScript types, right?
I know it doesn't as of now, but would it be possible to do so in the future to find some kind of hints or something?
Maybe I think one of the biggest problem is that we are building something. We are using something built in C++ to predict something that is written in JavaScript. So that's also a big problem. And the thing is that everything happens in runtime, and by nature of JavaScript, so they have a lot of nuances in JavaScript. So it's really hard to predict all the different use case and an exception that could happen in the language itself. So to map all of those into JIT compilers took years, and and they are creating new JIT compilers. So if you create a new JIT compilers, well, maglev is simpler than TurboFan for sure. It is a simpler way for optimization, but still it's new software, so they will have bug no matter what. Yes. Any other question? Nope. Cool. Thanks everyone.